Okay, good morning, everybody in 270. Welcome to the second last lab of this semester, Lab 7, Spatial Analysis 1. So in this lab, we're going to be using a different program, not using JASP anymore. The last two labs, we're going to use an application called Geog, which allows quite a few different statistical spatial stat tests to be done. So we're going to be doing all of these different tests and applications over the next two labs. So just a partial list of some of the things we're going to be doing in GeoLab here. We're going to be looking at spatial data sets. We're going to be looking at, in particular, a spatial data set for the country of Nepal. And to analyze this data set, we're going to be creating weight matrices, queen and rook matrices, which basically tell GeoDA how to analyze the spatial data. And why we're creating these spatial matrices is to run tests like Moran's eye and other tests that allow us to determine whether there is autocorrelation, aka clustering, or not within the spatial data itself. So some of the key terms, we're going to be doing a Moran's eye, Getty's G next time. And so some of the materials, or the main materials for this lab, is downloading the zip file, which is in the Moodle folder. It's called Nepal 2010. And so basically you just have to download it, unzip it, and that'll extract the contents and just put that somewhere on your computer where you can upload it to GeoDA. So this is what it looks like in the Moodle folder. If you haven't downloaded GeoDA yet, right, there's a URL. You can go to there to download it, whether you have Mac, Windows, or running a Linux. There's the zip file that you need to download and unzip right there, which contains all the spatial data. And here's a snapshot of the GeoDA interface itself. So at the top, like with most things, you have a menu, drop-down menu, and a lot of the functions that are in the drop-down menu have shortcuts in terms of these icons right here. And GeoDA is basically set up like most other spatial analysis software GIS packages, where you have a window to visualize your data. And then on the side panel, you have a legend. So the first thing you're going to do once you have your zip file downloaded and everything extracted is that you're going to be basically putting the file into GeoDA. So there's a couple ways you can do it. You can search through once you open up GeoDA, you can search through your directory and find where you put the shape file, or you can drop it directly into this box right here. So just keep in mind that we're dealing with, in this case, a shape file. And a shape file is a file basically which is made up of a spatial file, which is made up of a series of points or lines or polygons, right, which represent areas, linear features, or points, right? So it contains spatial data that you can visualize, but it also, for each of those features, the points, lines, and polygons, it also has a number of other non-spatial attributes contained within them. So for our data set, we're looking at Nepal. So once you get the Nepal opened up in terms of the map in GeoDA, you'll see that the country of Nepal is divided into a number of polygons. And within each of these polygons, you're going to have a number of attributes that we're going to be looking at. But we're going to be looking at more closely three attributes in particular. That is ALF, which stands for adult literacy rate for females, CPR, which is the contraceptive prevalence, and then DN, which is the population density. So there's a number of attributes for each of those polygons within the shapefile, but these are the three main variables or attributes that we're going to be looking at in this lab in particular. So getting into the lab itself, first thing you're going to do is just make a simple map of the shapefile, right? So you're going to use that button right there. And then you're going to basically save by right-clicking on the map itself, saving it as one of the image file formats shown below, listed below, and then just upload that into the Dropbox for question 1. Question 2, you're going to create another map. So you're going to go to the menu, go to map, go to themeless map, and this will open up another instance or another version of the map you already have open. So on your desktop, on your screen, you'll have two maps of the shape files. And the purpose of the question 2 is to analyze the classification of data for two different variables. So the first one, you're going to be making a classification map of CPR, right? And you're going to set it to quantile in terms of the classification, which will give you 4 different classes. And then you're going to make another map, right, by opening up another map and then setting your quantile again to 4 classes for the variable of ALF. So once you have those maps created, you're going to again right-click, save them, and then you're going to upload them in terms of image files. So this is basically what your maps are going to look like. So it just gives you a way to visualize the data in terms of the two main variables, the CPR and the ALF. So those are the two maps you're going to be submitting for question 2. Question 3, for the variable of ALF, you're going to be creating a histogram, which shows you a bit of the spatial stats of the data itself. So again, the variable is going to be ALF. You're going to go into the Explore tab and select histogram within Geog, and your histogram will be made. And then you can also right-click on the histogram and you can view some basic stats. So if you go up and hit Display Stats, it'll output some of the basic stats for the data below it. And that's what you're going to be using, that table below it, to answer questions 4 and 5. Basically stating what is the mean rate of female literacy in Nepal, providing your answer to 3 decimal places. Also looking at the histogram, how many districts have less than 10.1% ALF. So those would be read directly from the stats itself. Questions 6 and 7 deal with creating a box plot and analyzing a box plot. So you're going to be creating a box plot, right? And one key thing to know about the box plot is that as you scroll over top of the box plot, over top of the dots in your box plot, as you scroll over top of the different dots, those will highlight the areas within the map itself. So that's a way of connecting the point on the box plot to where it is in the map itself. Next thing you're going to be doing is creating a spatial weight file. Okay, and the spatial weight file is designed to tell Geog how to analyze spatial data. So to do this, you're going to go to the Tools tab, select Weights Manager, and then Create. This will allow you to create a weight file. So of course, you're going to be using the GDAN Nepal shapefile, the one that you already have open, Nepal 2010. Once in there, you're going to select the district as the ID variable. And so this will base the weight on the district locations. And the type of weight file you're going to create, first of all, is the Queen's contiguity. Okay. Leave the order level at 1 and then hit create, and this will create a weight file. So just a reminder from the lectures is that the difference between a weight file that follows a rook pattern versus a queen pattern, right? So the rook pattern in a weights file basically analyzes the 4 cells to the left and to the right, directly up and down, side to side, from the cell or grid point in question. While the queen, when you're making a queen weights file, it analyzes also the cells that are in the corners. So a queen weights file analyzes more cells surrounding the point in question compared to a rook weights file. So this is what it'll look like when you open up the weights manager, right? You'll be asked to create a couple different weights, right? One's called weight queen, one called weights rook, based on those 2 types of weights. And then you can look at what's called the connectivity histogram, which shows you how many neighbors you have based on using a queen's weighting or a rook weighting. So for instance, with the queen's weighting, the greatest number of neighbors, right, for a cell is 4. Most cells have 4 neighbors, but in terms of using a rook weights file, the greatest number of neighbors for a cell is 3. So you can see that there's similar patterns using a queen's weight file versus a rook weights file, but there are differences in terms of how many neighbors each cell has using those different weight files. Then you'll be asked to create a connectivity map, which allows you to visualize how the polygons are connected to one another. This, of course, is not for the Nepal data that we're looking at, but it's just a screenshot of a connectivity map made for polygons of Japan. And then the last part of the lab, we'll be doing a Moran's eye test. So again, Moran's eye is one of the most commonly used tests to determine whether we have spatial autocorrelation clustering in our data set or not. So the way that we analyze a Moran's eye index is that we looked at both its z-score and its p-value to see if it's significant or not. So the null hypothesis, and we can treat the Moran's eye or the Moran's eye test as a classical statistical test. We have a null hypothesis is that, and the null hypothesis with the Moran's eye is that our data is spatially arranged randomly. Okay, it might appear that there are some clustering or some dispersion going on, but our null or default hypothesis is that our data is randomly dispersed. Okay, and it's only when we discard or reject that null hypothesis is that we're going to say our data is either clustered or it is uniform, more uniform than you would expect by a random arrangement. Right, so again, our null hypothesis with spatial autocorrelation with the Moran's eye test is that there's no autocorrelation clustering going on. And then if we reject that, we either say we're going to have a negative spatial autocorrelation, a more uniform distribution of points, or we're going to have a positive spatial autocorrelation, which is basically clustering. Right, so to run the Moran's eye analysis in Geog, you're going to click the space tab and then select the univariate Moran's eye because we're going to be just looking at the one variable of CPR. And we're going to be using the weight file, which will basically tell Geog how to do the Moran's eye test. We're going to be using the weight file, the Queen's weight file that you made in the question previous. Then click OK. And so again, we can treat the Moran's eye as any other statistical test in terms of the null hypothesis being a randomly distributed data set. And then if we have a positive Moran's eye, and the Moran's eye is the stat that we get, the main stat that we get, if we have a very high I, that indicates that we have a clustered data set. If we have a very negative I, that indicates that we have a more dispersed data set compared to the null hypothesis. So how to interpret the output from a Moran's eye? Again, we're looking at the Z value and the p-value. So if we get a p-value that is not statistically significant, a relatively high p-value, say over alpha level of 0.05, we're not going to reject the null hypothesis. We're going to stay with the null hypothesis that our data is randomly distributed. If we get a p-value which is very low, it's significant, and the z-score is positive, aka the Moran's eye is positive, that means we're going to reject the null hypothesis and we're going to say that our data is spatially clustered. Again, if we get a significant p-value, very low p-value, and our z-score or Moran's eye is negative, again, we're going to reject the null hypothesis, but this time we're going to go with the alternative hypothesis that our data is uniformly dispersed. So the output from Moran's eye test in Geog is this scatter plot right here. And basically what this scatter plot here is analyzing is the value of CPR at any given location versus the lag CPR. So the lag CPR is the data value of CPR in the next polygon. So it's basically analyzing the value of CPR in one polygon and comparing it to the values of CPR in the polygons around it. And so basically the Moran's eye gives you the scatter plot, and at the top here, there's our Moran's eye, right, of 0.446. So that's positive 0.446, and that's indicating we have a positive slope. So when we have a positive slope of Moran's eye, that indicates we're dealing with positive autocorrelation, aka clustering. So a better graphic here, right? If we have a positive slope to our Moran's eye, that indicates that we have data points which are clustered low values next to low values, with high values next to high values, right? Indicating that we have overall clustering going on. Alternatively, if we have a negative slope to our Moran's eye, that indicates that we have more values, low values next to high values, right? Different values next to other different values, mixed with high values next to low value. So negative autocorrelation, or more uniform or dispersed spatial configuration to our data. Right, so we can analyze the different parts of our scatter plot. So for this instance right here, the circled points that I've just highlighted there are all the points that have low values that are next to low values. In the green there, we have high values, which are next to high values. And then all the other points that aren't circled are outliers. But we can see the majority of the points in this case, right, are clustered because we have more like low points next to low points and more high values next to high values. So overall, positive autocorrelation or clustering going on. So that's how to interpret the Moran's eye in terms of what type of autocorrelation you have. And of course, if you have a flat slope to your Moran's eye, that indicates that you probably do not have any autocorrelation going on. The other part of the Moran's eye is the p-value. So in Moran's eye, the way the p-value is generated is that you have an observed distribution, which is your variable for the Nepal shape file. And you're comparing that to a spatially random distribution, which is auto-generated by Geog. So Geog will, based on how many permutations you set, whether that be 499 or 999, it'll do all of those permutations, those calculations of a spatially random data set, and compare them to your observed distribution to see if your observed distribution is significantly different from the 400 or 1,000 permutations. So this is how the p-value is generated in Geog, and it's called a pseudo p-value because it's generated using computed spatially random distributions and comparing that to the observed. And so the output of this analysis, right? So for instance, imagine here what I've circled is the spatial distribution of my data set. And this kind of quasi-normally distributed bell curve, those are all the 999 permutations I've generated using Geog. So I can see here, we can interpret this kind of like a normal distribution. My observation is way outside of what anything I would expect. And you can see it gives me a pseudo p-value, which is very low, 0.001, meaning that, say, if I set an alpha value of 0.05, I'm definitely going to reject the null hypothesis and assume that my data is not normally distributed. And then based on that, right, by looking at your pseudo p-value, you're going to determine whether you're going to reject or retain the null hypothesis. And based on the value of the Moran's eye, you're going to determine whether you have positive autocorrelation, aka clustering, or negative autocorrelation. And that is it for today's lab. So only one more to go. We'll talk a little bit more about spatial autocorrelation in the lecture later on this week.